In this week's topics, we'll be talking about things called vector spaces. This will be some new territory for most of you, and so before we get to the main event, we're just going to build up to it conceptually a little bit. We're going to talk about how we organize similar mathematical things, and that'll make more sense in a minute, and how we can actually redefine operations that you already know and use, but maybe we want to change them up a little bit. So don't worry about this too much. It's going to seem unfamiliar, and it might seem a little more advanced and conceptual, and it is a little more advanced, and it's definitely more conceptual. So instead of just calculate this or that, we'll be looking more at problems of categorization and definition. But basically, this is where I will be showing you how all the stuff you already know about and know how to do aren't really special by themselves. They're just specific cases of broader concepts. So first of all, the phrase vector space itself, we're going to be talking about them. You might not have heard the phrase before. It sounds very Star Trek-y, but you already work in vector spaces. So every time you work with a real number, a polynomial, a matrix, a function, a vector, they're all parts of vector spaces. And so what we do is we collect similar things, we assign some rules, and sometimes those rules hold up to the point where we've formed what's called an official vector space. So you already know about vector spaces and you've worked in them. You just might not have called them that before. So first of all, let's talk about what it means to gather similar mathematical objects. Well, think about just saying, I'm going to pull together all integers, or I'm going to gather all positive real numbers, or I'm going to gather all 2x2 matrices. So what we're doing is we're making gatherings, making groups of similar things. Maybe we're going to gather just diagonal 4x4 matrices. We can do that. Or polynomials of degree 2, or we can go out there to the universe of all functions that are available and say we're going to rope together the functions that happen to be continuous on the interval from 0 to 1. We're going to pull together functions that go through the origin. I mean, you can sit here and play this game all day. Think about similar mathematical things and gather them up. Having gathered up something, some collection of stuff that's similar, what we have to do is define how the members of this club, this gathering, talk to each other. And this is going to be a little bit weird because we're going to define rules called addition and scalar multiplication. And now at this point you're saying, well, wait a minute. I already know how to do addition and I already know how to do scalar multiplication. What do you mean we're going to define these things? Okay, well, this is actually the point. The definition of addition and scalar multiplication that you've been working with all your life is just one of many possible definitions of addition and scalar multiplication. So that little plus sign that you use for addition is really just a symbol. It has any meaning we want to ascribe to it. All your life, you've ascribed a particular meaning to it, but we can change that meaning. Or we can go over to the world of 2x2 matrices. Now, you already think you know how to add two matrices together, but maybe we want to change what that little symbol means. So rather than adding up all the components, maybe we would like to define addition to mean if we take two 2x2 matrices and add them, we get back a frog. Okay, well, we can do that. Some of these redefinings will make more sense than others, and sometimes the redefinings will make so much sense that we will create a new vector space. Okay, so let's look at an example. So we're tired of using the same old rule for adding two matrices together. You know how to add matrices together using the regular rule. And so if you were faced with these two 2x2 matrices, you know what you would do. You would add up all the components in the four individual spots, right? Well, we're going to change that a little bit. We're going to say addition of 2x2 matrices is now going to mean this. The diagonal always becomes 0. No matter what the original entries were, but then we are going to add up the individual entries in the off-diagonal elements. Okay, there we go. We've redefined addition on 2x2 matrices. And we'll keep scalar multiplication the same because let's not do too much at once. All right, so now we have a new system. We've gathered 2x2 matrices and we've defined what we're going to refer to as addition and scalar multiplication. It's a little bit different than what you've defined it as before, but it's still perfectly okay to do this. Here's a specific example, right? Now we're going to add these two 2x2 matrices together, and the new result, again, the diagonals just automatically become 0, and then the components still add up off the diagonal the way they used to. So you can follow the red numbers and follow the blue numbers and see why they work out. Scalar multiplication again, same old, same old. So there you go. There's our new system. The big question that we're going to answer in the next slides is, having made this new system, did we create something awesome, or did we just create something silly? But here's a different example, right? Here's polynomials of degree 3, polynomials that go up to x cubed. They have any old coefficients that we need them to have. This time, we are going to define addition on polynomials and scalar multiplication like this. Addition of polynomials will now mean that we will take the coefficients of the first polynomial to the left of the plus sign and subtract the coefficients of the polynomial to the right of the plus sign. So that's a brand new definition of quote-unquote addition. And our new definition of scalar multiplication is go down the polynomial and multiply every other coefficient by that scalar. So we have a new system. We've got all the polynomials of degree 3. We have a brand new addition and a brand new scalar multiplication. As an example of how this would work, here's two specific polynomials. Let's add them together. So again, the coefficients of the first polynomial minus the coefficients of the second polynomial. Notice that one of the coefficients in that second polynomial is 0 because there is no x to the first term. Take a second to see how this works out. And here's an example of scalar multiplication. We're doing 3 times the polynomial p. Our new definition means we're going to multiply every other coefficient by 3. Right? So there we go. Brand new system, polynomials of degree 3 with new addition and new scalar multiplication. Did we make something awesome, or did we make something silly? Well, that's for the next section to tell us. Vectors with 4 components, where the second and fourth are 0. That's our collection. So we're going to gather all 4-dimensional vectors that look like this. Here's how we're going to define addition and scalar multiplication. V plus W will now mean the product of V1 and W1, the first coefficients, and the product of V3 and W3, the second coefficients. And scalar multiplication means we're actually going to add the scalar C to the first and third components. Okay? It's not addition and scalar multiplication the way you're used to seeing it. We don't care. We can do whatever we want now. We are in charge. We are in charge of the plus sign, and we are in charge of scalar multiplication. So for these two, add them up. That means multiply the first and third coefficients and put them in the proper spots. And then scalar multiplication means add the constant to the first and third terms. Now notice in this example and the others that we're redefining addition and scalar multiplication, but we are returning another item of the same type. So even though V plus W is defined very strangely, we're still adding together 4-dimensional vectors and returning 4-dimensional vectors with that operation. Okay, one last example. We're just going to pull together all the real numbers. But regular addition and scalar multiplication, we're tired of that, so let's switch it up. So u plus v will now be the product uv, and scalar multiple k times u will be u raised to the k. So 3 plus 5 is now 15. 2 times 4, the scalar 2 times the real number 4 is 4 squared, or 16. We can do this. We are in charge. So the open question all along is, yes, we can make all these systems that are different than we're used to, but we are in charge. We're allowed to do that. Have we made something that holds together, that's internally consistent, or did we just make nonsense? So what's going to happen is there's going to be 10 rules we have to check our new systems against. Do the elements in the system together with the new addition and scalar multiplication hold up against these 10 rules? If so, we have made a vector space. And if not, we just made something silly. The 10 rules are going to ensure that the system is internally consistent, that there will be items in the space that we know need to be there. We'll talk about those in the next set of slides, and that the members of the system play nicely with each other. In the process of learning these 10 rules, you're going to learn why, way back in the day, you had to learn about all these phrases like associative and commutative and distributive. You learn these words and you never saw them again. Well, they're actually properties of vector spaces. And of the 4 examples we just did that were kind of silly, it turns out one of them actually does make a vector space. Even with the silly appearance of the new additions and scalar multiplications, one of those 4 actually produces something awesome. So let me repeat what we started with, that all your life you've been doing vector space stuff already. You've been doing addition, you've known how to do scalar multiplication, you've worked with elements of vector spaces. You just didn't know it because you probably didn't use the phrase. But the set of all real numbers with addition and scalar multiplication defined as you're used to using them, that's a vector space. We've been talking about matrices. So for example, the set of all 2 by 2 matrices with addition and scalar multiplication as you were used to it is a vector space. Polynomials of degree 2 with the usual operations is a vector space. Okay, so we already know all this stuff. The fun things happen when we redefine the addition and the scalar multiplication, and that's what we're going to go to next.